Hey, welcome back, folks. In this video, we're going to look at trigonometric integrals part 2, how to evaluate trig integrals when we have even powers of sine or cosine. Recall in trigonometric integrals part 1 video, we saw odd powers of sine or cosine. So to continue here with the even powers of sine or cosine, we're going to return to guidelines that were first presented in the first video. There were two guidelines given there, and here we finish off the guidelines with the third and final guideline. If your powers of sine and cosine are even and non-negative, what we're going to do is we're going to make repeated use of the power reducing, or also known as the half angle, identities. Now, the power reducing, or half angle identities, are simply sine squared x equals 1 minus cosine 2x over 2. But I like to look at this as a 1/2 times the quantity 1 minus cosine 2x. And then cosine squared x is a 1 plus cosine 2x over 2. And I like to look at that as a 1/2 times the quantity 1 plus cosine 2x. I think once we do an example and we start integrating, you'll see why I prefer the version I do. So let's look at the following example. Let's say we're asked to determine the antiderivative of sine to the fourth x dx. Well, we begin this with a pretty easy step. Sine to the fourth x dx. That's just simply sine squared x times sine squared x dx. Now here's where we make use of our power reducing identity for sine squared x. In fact, we're going to use it twice. For this sine squared x, we use the power reducing identity 1/2 1 minus cosine 2x, and we're using it for this factor of sine squared x as well. 1/2 times 1/2 gives us 1/4. Since that's a constant, we can rip the 1/4 out in front of the integral sign. Then when we take a 1 minus cosine 2x and multiply it by 1 minus cosine 2x, we're going to get a 1 minus 2 cosine 2x plus a cosine squared 2x. But notice right here, cosine squared 2x, we have an exponent of 2. So a natural question would be, can we use the power reducing identity to reduce this down? And the answer to that question is yes. We can take that cosine squared 2x and we can reduce it down by using our power reducing identity. But there's one caveat. Our power reducing identity says cosine squared x is equal to 1/2 quantity 1 plus cosine 2x. So when we're going to use this identity on cosine squared 2x, we have to make sure that there's a 2x here and there's a 2x here. So if we continue with our example, notice when we put the 2x in for the x's, we get cosine squared 2x equals 1/2 quantity 1 plus cosine of 2 times 2x. So if we continue with the integral that we had, we're now this is the integral that we left off with, 1/4 times the integral 1 minus 2 cosine 2x plus cosine squared x. So if we continue with that, for the cosine squared 2x, we're going to put in the 1/2 1 plus cosine 4x. And many calculus books will just go from this step to this step, and maybe you're not quite sure where the 4 is coming from in the cosine 4x. Well, I hope now you can see exactly where the 4 is coming from. And taking care to do just a little distribution here. So we distribute the 1/2. 1/2 times 1 is 1/2, plus this 1 gives us a 3/2. There's the 1/2 cosine 4x. Continuing, the calculus should, I would hope for you by this point in time, the calculus would be really straightforward, that the antiderivative of 3/2 is a 3/2 x, Antiderivative of 2 cosine 2x is simply sine 2x. And finally, antiderivative of 1/2 cosine 4x is 1/8 sine 4x. And this is a good antiderivative for the problem we started with. But if we go ahead and distribute the 1/4, we could get a final answer of 3/8 x minus a 1/4 sine 2x plus a 1 over 32 sine 4x plus c. And this concludes trigonometric integrals part 2 on how to integrate a trig integral when we have an even power of sine or cosine. I hope this video, in conjunction with video 1, trig integral part 1, I should say, I hope it illustrates that when you're integrating trig integrals involving sine or cosine and the different powers of sine or cosine, that actually doing these trig integrals, well, it's not that difficult and it's not that bad. Thanks for watching.